Hey everyone, and welcome back. Today we're going deep on LLMs.
Those large language models
Yeah, those things,
that are changing?
pretty much everything.
Yeah, pretty much everything.
But there's always a challenge, right?
Right.
With great power comes great responsibility and all that.
Right. And one of the big challenges is memory.
LLMs need memory
Really shine.
yeah, like if they're going to analyze a long document or they're going to have a conversation,
That spans multiple topics or turns.
they need to remember a lot of information.
Yeah, traditional LLMs, they're kind of like sprinters.
Oh, like amazing for short bursts.
Yeah, short bursts, but
Not built for marathons.
not built for marathons. Their ability to remember previous information.
That's the context, right?
That's the context, and it's limited.
So they struggle with those really long pieces of text.
Exactly.
So they might be great at summarizing a news article,
Mm-hmm.
but if you ask them to tackle War and Peace,
Yeah,
probably not going to happen.
not going to happen.
So that's where LeMo comes in.
That's where LeMo comes in.
And you sent me a ton of research on LeMo.
Yeah, I did.
So let's break it down. LeMo is designed to make LLMs those long context champions,
Exactly. So it can fine-tune those LLMs to handle those marathon tasks.
but without needing like a supercomputer.
Yeah, and it does it by using this clever trick.
A trick?
Yeah, tapping into this natural redundancy of language.
Okay, so remind me what fine-tuning is again.
Hmm.
It's like giving an LLM a specialized training course.
Exactly.
We're not building a new LLM.
No, we're taking an existing
Taking one that already exists, and we're saying, okay, you are now an expert in
this specific area,
and in this case,
handling a ton of text.
okay, so what's the potential here?
So think about LLMs that can analyze massive documents. Like
A
imagine,
100-page contract.
yeah, and instantly grasp all the nuances.
Okay.
Or imagine AI assistants that can actually follow a complex conversation.
So they can actually remember all the details.
All the details that you've discussed.
And then what about like handling complex code bases?
Yeah, LeMo-powered LLMs could understand
A whole software project.
the entire software project.
So they could help developers
Advice.
find bugs, even suggest improvements.
Just improvements.
Okay, that's some serious potential.
Yeah.
But I'm looking at all this research and just trying to fine-tune an LLM for these longer contexts using those traditional methods seems
It's intense.
intense. It's like
trying to fit an entire encyclopedia into a tiny backpack.
yeah.
The memory demands are just huge.
Yeah, I was looking at one of the papers on this method called position interpolation.
Oh, yeah.
And they were saying that they needed 128.
100 GPUs?
Those are some seriously top-of-the-line processors.
Oh, yeah.
Just to extend the context length to 32,000 tokens.
That's a lot.
My laptop would melt.
Yeah.
So how does LeMo pull off this long context magic without needing a server farm?
Okay, so here's where it gets interesting.
Okay.
LeMo works on this principle that language is inherently repetitive.
Okay.
We say the same things in different ways.
Yeah.
We repeat information. We use a lot of filler words.
Uh-huh. And LeMo identifies and eliminates these redundant tokens
During the fine-tuning process.
during the fine-tuning process itself.
Okay, so LeMo is like that super efficient note taker
Yeah.
who can listen to a 2-hour lecture.
And distill it down into a single page.
It's getting rid of all that fluff, focusing on just the essential stuff.
Exactly.
So LeMo, this is where it stands out.
This is where it stands out.
It's the first system to leverage this
Contextual token sparsity
contextual token sparsity.
during the fine-tuning process.
Oh, okay.
And that's what makes it so efficient.
Okay, I'm following you so far.
Great.
But walk me through the mechanics.
Okay.
How does LeMo actually decide which tokens are essential and which ones can get tossed?
So LeMo has a 3-step process.
3-step process, okay.
The first one is called token elimination.
Token elimination.
So it analyzes the text and it identifies those redundant tokens that don't really add much meaning.
So it's like skimming a book and highlighting only the key sentences.
So it's not just compressing things after the fact. It's actually getting rid of those unnecessary tokens during...
The fine-tuning process.
Okay.
But analyzing every single token in this huge text would take forever, right?
Oh, yeah.
So that's where the second step comes in.
Okay.
It's called pattern prediction.
Pattern prediction.
And LeMo learns to predict which tokens are likely unimportant
Based on the words around them.
based on the surrounding context.
So it's like reading a mystery novel and learning to spot those red herrings.
Exact.
Those clues that seem important, but they're really distractions.
Exactly.
LeMo is developing this instinct for what's truly meaningful.
Yeah, it's figuring out what matters.
Yeah.
And then To make the whole process even more efficient, there's a third step.
There's a third step.
It's called kernel optimization.
Kernel optimization.
And this gets down into the nitty-gritty of the software itself.
Okay.
So it optimizes the code,
To reduce memory usage?
reduce memory usage, and speed things up.
So it's not just about clever algorithms. It's about streamlining the software to run as efficiently as possible.
Exactly.
Okay, this is all incredibly cool, but does it actually work? Like, what kind of results are we talking about here?
Okay, so the results are pretty remarkable.
Right.
LeMo can achieve memory savings of up to 1.93 times compared to traditional fine-tuning methods
So it can handle double the sequence length.
without needing a room full of servers.
And it can be combined with other techniques?
Yeah, to make things even more efficient.
Okay, so it's not just a one-trick pony.
No, it's a team player.
It's a team player.
It is.
This is starting to sound like a real game changer for anyone working with LLMs.
Absolutely it is.
Okay, you mentioned this thing earlier called shadowy activation.
Oh, yeah.
That sounds a little ominous.
It's not as scary as it sounds.
Okay.
Imagine a crowded room
Okay.
where even people just passing through take up space.
Okay.
Existing methods for making LLMs more efficient.
Even the ones that introduce this thing called sparsity.
Even those ones, they still suffer from this.
Yeah.
They might reduce the amount of interaction between people.
Yeah.
But everyone is still present.
Yeah.
And they're still taking up memory.
So even if you're not talking to everyone in that room, their presence is still affecting the overall space.
Yeah, it's like a memory leak, but for people.
Well, that's a good way to put it.
And that's what LeMo solves so brilliantly.
Okay.
By completely eliminating those unnecessary tokens, it's not just reducing the interaction, it's actually shrinking the crowd itself.
So that's what leads to these really significant memory savers.
That's exactly it.
Wow, this is making me rethink how I approach information overload in general.
Yeah.
Maybe I need a LeMo upgrade for my brain.
Maybe that's a deep dive for another day.
Another day.
But one thing that really jumped out at me from these papers is how LeMo was tested across different LLM architectures,
Yeah.
like OPT and Llama, and on different hardware,
So that suggests that it's got,
real-world applicability.
okay, and it's not sacrificing accuracy for speed and memory gains, right?
That's a big takeaway.
LeMo is not just making things faster and leaner. It's doing so without compromising on the quality.
That's exactly right. It speaks to the elegance of LeMo's approach.
All right.
It's tapping into something fundamental about language itself,
Okay.
using its inherent redundancy to achieve both efficiency and accuracy.
Okay.
It's like finding a shortcut through a dense forest that not only gets you to your destination faster,
Yeah.
but it offers a more scenic route.
Okay, I'm sold.
Good.
LeMo is clever, it's efficient,
Mhm.
and it opens up all these new possibilities for LLMs.
Absolutely.
But before we get too carried away, I have to ask, are there any downsides or potential risks
Oh, that's a great question.
associated with LeMo? Because every new technology has its trade-offs, right?
You're absolutely right. And because LeMo is relatively new, there's still much to learn about its long-term effects and how it interacts with different types of data.
Sure.
It's like any new tool,
Yeah.
we need to use it wisely and understand its limitations.
So it's a bit like navigating uncharted territory.
It is.
But that doesn't diminish the excitement around its potential.
Absolutely not. LeMo is a significant step forward in how we can utilize LLMs. And it really speaks to the ingenuity of the researchers that are pushing these boundaries.
Of what's possible with AI.
Exactly.
And it makes me wonder if LeMo can pinpoint these most crucial parts of a text during that fine-tuning process.
Yeah.
Could that tell us something about how we learn and how we process information as humans?
Now, that is a fascinating thought,
Do our brains have their own token elimination system
right?
for filtering out all that noise? It's like that idea that compression is intelligence,
Yeah.
being able to distill complex information down to its essence.
Whether it's a machine or a human brain doing it,
Yeah,
it's a hallmark of true understanding.
and that's maybe the most intriguing aspect of LeMo. And just the whole field of LLMs in general.
Yeah.
We're not just building machines that can process language. We're
Right.
potentially unlocking new ways.
Of understanding thought itself.
Well said.
Thank you.
I think we've covered a lot of ground in this first part of our deep dive.
Yeah, we have.
Let's take a moment to process all this information.
Yeah.
And then we'll be back to delve even deeper into those technical nuances of LeMo
Okay.
and what its success could mean for the future of AI.
Sounds good. Welcome back.
Okay, so let's zoom in on some of those technical hurdles LeMo had to overcome.
Yeah, like how does it actually figure out
Yeah.
which tokens are redundant.
Because that's got to be more challenging than it sounds.
It is.
It seems like you could accidentally delete crucial information along with the fluff.
Right.
So how does LeMo make sure that it's not throwing the baby out with the bathwater?
Okay, so LeMo uses this concept called
Token informativeness.
token informativeness to decide which tokens are worth keeping.
Okay.
It's not just about how frequently a word appears,
Okay.
but it's about its contribution to the overall meaning,
Got it.
taking into account its relationships with other words.
So it's not just about who has the most lines in the play.
Right.
It's about who's actually driving the plot.
Exactly. And this informativeness score,
Okay.
it's determined using what's called the attention mechanism,
Okay.
which is a core part of how LLMs work.
Oh, yeah. The attention mechanism.
So it's essentially a way for the model to focus on the most relevant parts of the text.
So LeMo is tapping into the LLM's own internal focus system.
Yeah.
To figure out
which tokens are important.
which ones are the real heavy hitters.
Exactly.
Okay.
And it adapts its strategy based on the specific layer
Oh, right. The layer
of the LLM that it's working on.
Can you remind me what those are in the context of LLMs?
Okay, so think of an LLM as a multi-layered cake.
Okay. A cake. I like cake.
Each layer represents a different level of processing.
Okay.
So the bottom layers handle the basic language understanding,
Like recognizing words.
and the top layers are responsible for more complex tasks.
Like understanding the relationships between ideas.
Exactly.
So the bottom layer might be focused on like identifying the individual ingredients in a recipe.
Yeah.
And then the top layer is figuring out how those ingredients work together.
To create the final dish.
Okay.
A perfect analogy.
I like it.
And LeMo is smart enough to adjust its approach.
Okay.
And depending on which layer it's working on.
To make sure it's always finding the right balance.
The right balance between removing that redundancy
Uh-huh.
and preserving the accuracy.
That's amazing.
Yeah.
It's not just blindly deleting data.
Yeah.
It's understanding the inner workings of the LLM.
Right.
And making decisions based on that knowledge.
Informed decisions.
It's like a surgeon, not a butcher.
I like that analogy.
Okay, so back to the technical side of things.
Yeah.
You mentioned that LeMo takes this block-wise approach to token elimination.
It does.
What does that mean?
Okay, so it's all about maximizing efficiency.
Okay.
Instead of analyzing each token individually, which would take forever.
Right. LeMo groups tokens into these blocks.
Right.
And then it analyzes them as a whole.
So it's like reading a book a paragraph at a time.
Exactly.
Rather than word by word.
Yeah. Great analogy.
And this allows LeMo to process information
much faster
without losing that precision.
Without losing precision.
And this ties back into that kernel optimization you were talking about earlier.
Yes, it does.
Making that software itself
run as smoothly as possible.
Okay.
The developers behind LeMo, they didn't just stop at the algorithms.
Yeah.
They dug deep into the code itself.
Okay.
Optimizing it to minimize that memory usage and to speed up that processing.
It's incredible how much detail goes into developing these systems.
It is.
It's like they're not just writing code. They're crafting like a high-performance engine.
And that attention to detail is what makes systems like LeMo possible.
Okay.
It's not just about a brilliant idea.
Yeah.
It's about meticulous execution and a relentless pursuit of efficiency. It seems to be paying off.
Yeah.
Based on those results.
Yeah.
But before we move on, I am curious about how LeMo handles the training process itself.
Okay.
Because that's where things can get really demanding.
Yeah.
Especially when you're dealing with these longer contexts.
You are absolutely right, training an LLM.
Yeah.
It's computationally intensive, even more so with longer contexts.
Right.
But LeMo incorporates several techniques to address this.
Like what?
Remember pattern prediction?
Yeah.
That plays a really crucial role in training as well.
So LeMo learns to anticipate which tokens are unimportant.
Right.
Based on the surrounding words.
Exactly.
But how does it learn those patterns in the first place?
So it utilizes these lightweight neural networks, essentially smaller, specialized AI models, to learn these patterns. And these networks are trained offline, meaning they can learn from massive amounts of data before they're even integrated into LeMo.
So it's like giving LeMo a cheat sheet.
Yeah.
So it doesn't have to start from scratch.
Exactly. And the offline training itself. It's optimized using a technique called elastic size transformation, which streamlines those neural networks.
So we're trimming the fat every step of the way.
We are.
I'm loving these analogies, by the way. They're making all this complex stuff so much easier to understand.
Oh, I'm glad.
But let's get back to LeMo's training process. One thing that really stood out to me was its use of segment-based peak cutting
Yes.
to manage that memory usage.
Exactly.
What exactly is peak cutting?
Okay, so imagine you're trying to fill a bathtub
Okay.
with a limited amount of water.
Okay. A bathtub, limited amount of water.
If you turn the faucet on full blast,
Uh-huh.
you might overflow the tub before it's even half full.
Makes sense.
But if you reduce the flow rate,
Okay.
you can fill the tub completely
Without wasting any water.
without wasting any water.
So peak cutting is about carefully managing the flow of information during training so you don't overload the system's memory.
Precisely.
It's like load balancing for the brain.
It is.
So even though LeMo is handling these much longer contexts, it's doing so in a way that's super efficient.
Super efficient.
And memory aware.
Exactly. And that's one of the key reasons why LeMo is so exciting.
Okay.
It's not just theoretical improvements.
Yeah.
It's about practical solutions that can be implemented on real-world hardware.
Without needing all those massive computational resources.
Exactly.
I'm seriously impressed. LeMo is shaping up to be a real game changer.
Yeah.
But before we crown it the champion of LLM optimization,
Right.
I am curious about its real-world applications.
Yeah.
Are there any examples of LeMo being used in practice?
That's a great question. So since LeMo is relatively new, it hasn't been widely deployed in commercial applications just yet.
Sure.
However, the research papers highlight its potential across a whole range of tasks.
Like what?
Document analysis, dialogue systems, and even code comprehension.
So we've got this shiny new tool.
Yes.
And we're just starting to figure out all the things it can do.
That's a great way to put it. And the research community.
Yeah.
They're buzzing with excitement, exploring LeMo's potential.
In all these innovative ways.
In all these innovative ways, and there's some fascinating work being done. Combining LeMo with other optimization techniques.
Okay, you mentioned earlier that LeMo plays well with others.
It does.
Can you give me some examples of how it's being combined with other approaches?
One very promising area is combining LeMo with techniques that exploit sparsity at the hidden dimension level.
Okay. You're going to have to remind me about hidden dimensions.
Of course.
My linear algebra is a little rusty.
Okay, so imagine you're describing a person.
Okay. Describing a person?
Yeah. You might talk about their height, their weight, hair color, eye color, and so on. Each of these attributes represents a different dimension of that person's overall description. Now, in LLMs, each token is also represented by a set of values. Which we can think of as its hidden dimensions.
So, just like with a person's description? Some of those hidden dimensions are more important than others.
Precisely.
Like knowing someone's favorite color might not be as crucial as knowing their personality.
Exactly.
And traditional sparsity methods.
They try to eliminate those less important dimensions to make the model more efficient.
So it's like saying, we don't really need to know someone's shoe size to understand their political views.
Exactly. And the exciting thing is that we can combine LeMo with these hidden dimension sparsity methods to create what we call a two-dimensional sparsity approach.
Two-dimensional sparsity.
So we're eliminating unnecessary tokens. And we're getting rid of those unimportant dimensions within those tokens.
So we're squeezing the information from both ends.
Yes, we are.
That's pretty clever.
It is.
Are there any other examples of LeMo being combined with other techniques?
Another really exciting area is using LeMo to enhance offload-based techniques.
Offload-based? What are those?
So these methods involve moving data between the computer's main memory and its faster but more limited graphics processing unit.
Oh, the GPU.
The GPU. So it's like using LeMo to decide which data is important enough to stay on the express lane and which data can take the scenic route.
I like that.
By combining LeMo with these offloading techniques, researchers are able to train LLMs on even larger data sets and longer contexts without exceeding the memory limits of their hardware.
So it's like we're using AI to optimize AI. To handle even more AI.
AI inception.
It really highlights the incredible pace of innovation in this field.
It does.
We're constantly discovering new ways to push those boundaries of what's possible with AI.
And LeMo is a prime example of that. It's a testament to the ingenuity of these researchers. We're finding ways to make these powerful models more efficient, more accessible.
And ultimately more impactful.
Exactly.
Okay, I am totally convinced that LeMo is a force to be reckoned with.
Good.
But before we wrap up, I think we need to compare LeMo to other approaches
Yeah.
and see how it stacks up against the competition.
An excellent point. The papers you shared included some in-depth comparisons
Okay.
between LeMo and some other cutting-edge fine-tuning methods,
Okay.
like LoRa and long LoRa.
Okay.
So let's dive into those benchmarks and see how LeMo fares.
Okay. A little friendly competition always keeps things interesting.
It does.
And it's crucial to stay informed.
About the latest developments?
After all, that's what the deep dive is all about. Okay,
Yeah.
so it's like we've got this AI.
Championship bout.
Yeah.
In one corner.
The token sparsity champion.
Promising those big savings.
In memory and faster training times.
And in the other corner, we have...
LoRa.
And long LoRa.
Two of the most popular fine-tuning methods out there.
Some heavy hitters.
I've got my virtual front row seat ready.
Okay.
So what are the judges?
The researchers.
The researchers.
Yep.
What are they looking for when they compare these methods?
Okay, so they're focused on three main things.
Okay.
Memory footprint.
Okay.
Execution time.
Yeah.
And, of course, accuracy.
Okay, so we want a method that's efficient with memory.
Right.
Doesn't take forever to train.
Right.
And it still allows that LLM to actually do its job.
To perform well.
So it's like we're looking for the trifecta.
The trifecta.
Of efficiency and accuracy. Okay, let's start with memory.
Okay.
How does LeMo stack up?
Okay, so the results are pretty impressive.
Okay.
LeMo consistently outperforms both LoRa and long LoRa.
Okay.
When it comes to memory efficiency.
Okay.
Sometimes by a significant margin.
Okay.
One of the research papers included this table.
Okay.
Showing the memory needed to fine-tune different LLMs.
Okay.
On a single A800 GPU. So one GPU.
One GPU, and LeMo was able to handle sequences twice as long as the other methods.
Wow.
While staying within the memory limits.
Okay, so LeMo really is living up to its name as a memory saver.
It is.
But what about speed?
All right.
Does it sacrifice training time?
That's the best part.
Okay.
It doesn't.
It doesn't.
LeMo is actually faster than LoRa in many cases.
Okay.
And it's comparable in speed to long LoRa.
Oh, long LoRa.
Which is specifically designed
for long context.
For efficient long context training.
Okay.
And the graphs in these research papers, they show LeMo consistently achieving speedups of 10% or more.
Wow.
Compared to LoRa.
Okay.
And sometimes it even beats long LoRa.
Okay, so it's winning on memory and speed. Yeah. But the real test.
The real test.
To accuracy.
Accuracy.
Does LeMo's strategy of eliminating tokens?
Yeah, does it?
Hurt how well the LLM actually performs.
Okay, that is the crucial question.
Yeah.
And thankfully, the research gives us some reassuring answers.
Okay, across various benchmarks.
Like what kind of benchmarks?
Things like perplexity tests on long context data sets. Yeah. And evaluations on tasks like question answering and text summarization.
Okay.
LeMo shows comparable accuracy.
Okay. To
both LoRa and the original unoptimized LLM.
So it's not just faster, more efficient, it's just as good at its job.
Exactly.
It's like finding a way to make your car run on half the fuel.
Right.
But without sacrificing any horsepower.
I like that.
So I'm curious to see how combining LeMo with these other techniques might push the boundaries even further.
You are thinking like a true AI innovator.
And the answer is yes.
Yes, absolutely.
The research papers explore some really cool possibilities, like combining LeMo with methods that use sparsity.
At that hidden dimension level? Or using it to enhance those offload-based techniques.
Right, the two-dimensional sparsity.
Yes.
And the offloading.
Exactly.
Like we're creating a multi-layered optimization cake.
I love it.
What kind of results are they seeing?
The results are amazing.
Okay.
By combining LeMo with these other techniques.
Okay.
Researchers are seeing even greater performance improvements.
Okay, like how much greater?
Sometimes achieving speedups of 2 times or more.
Wow, so it's not just a solo act.
Right.
It's a team player that can really elevate the whole game.
It can.
This makes me so optimistic about the future of LLMs.
Me too.
If we're already achieving these kinds of gains now,
yeah,
imagine what will be possible in a few years.
It is a really exciting time to be working in this field.
It makes you think about the bigger picture, too.
Yeah.
We've talked about how LeMo might help us understand how our own brains work.
Right.
But what about its potential impact on society?
That's a crucial question.
Yeah.
As LLMs become more powerful and more efficient, their role in our lives will undoubtedly expand.
Okay.
We'll see them automating more tasks, personalizing experiences, creating new forms of art and entertainment.
And maybe even helping us tackle
some of the world's biggest challenges.
Exactly.
It's exciting and a little bit daunting.
Yeah.
It feels like we're on the verge of a new era.
It does.
And we don't even know what we'll discover.
That's the thrill of discovery.
But one thing's for sure.
What's that?
We need to approach this new era with enthusiasm.
Yes.
And careful consideration.
We have to make sure that these technologies are used for good.
Yeah.
And that they benefit all of humanity.
Absolutely. And I think that's a perfect point to wrap up this deep dive.
I agree.
We've explored a lot, from the technical intricacies of LeMo's approach
We have.
to those broader societal implications.
And these powerful LLMs.
Yeah, a huge thank you to you, our listener.
Yes, thank you for joining us.
For joining us on this incredible journey.
It's been a pleasure.
We hope you've gained some new insights.
I hope so.
Feel inspired.
Yep.
And will join us again for our next deep dive.
Into the cutting edge of technology.
Until then,
keep exploring.
Keep questioning. And keep diving deep.